Hello. So for today's class, we're gonna do uh, first the assembly of the global residual and tangent, and I'm gonna have two options to do that. And in a separate video, I'm gonna do the solution of one problem. So hopefully with that one, everything will come together for this class. So for the residual and tangent, consider the mesh. This is actually also a mesh that I used for the problem that I'm gonna solve later on. It has 8 nodes and 5 elements, 5 quadrilateral elements. I listed already the nodes because I just want to have the coordinates of each node. Doesn't matter how you number them actually. I just went counterclockwise and first the outer nodes and then the inner nodes, but there is no reason to choose a particular order. I will say once we come with to the issue of boundary conditions, which I'll do in option 2. So for this one, option 1 is not actually no, for option 1 I do need to know where the boundary conditions are. So that's going to be the tricky thing later on. So when we assemble the residual and tangent, actually let me put a note here. Anticipating solution for some nodes only. So recall that when we set up the weak form, we have w, a vector of w times this residual is going to be 0, right? So this is the scalar 0. This is our what happens with the weak form. So this is essentially the discrete weak form. Boils down to that. And this has to be true for all w with some condition, right? Let me move that here. So that has to be true for all w with w equals 0 at the boundary with essential boundary conditions. And because of that, not all the rows of this residual vector are important. And I kind of sketched it before, so basically you can get rid of those rows in the residual. So not all. So whenever w is 0, so for w equals 0, the corresponding row of R can be whatever, right? Can be non-zero because w is 0. So if w is 0, then when you multiply that with whatever is in that row of w, then the result will be 0, so you will be satisfying that equation. So actually, why is the residual non-zero at that point? Is because there is some reaction force or reaction flux, a reaction basically. So an unknown derivative for your field. So that's the main thing. So not all of the rows of w are 0. So we cannot solve when we say, so this implies, so w r equals 0 implies r equals 0, but not all the r, right? So this implies r. Here, let me put an asterisk. It implies r equals 0, but only for the rows of r that do not correspond to a node with an essential boundary condition. And that's the key thing. That if you assemble the entire residual vector, this vector will be size number of nodes. So this, if you just assemble this, so if you just do that, then this is size number of nodes. Obviously this is also size number of nodes. But again, because there's some nodes that have essential boundary conditions, and we know that for those nodes the w equals 0, and therefore the corresponding row of r is not necessarily 0. So this being true for all w's, including the ones that are 0 at the boundary where you have essential boundary conditions. Means that R has to be 0, but only for nodes that are not in the essential boundary condition case. So implement for all nodes that don't have essential boundary condition, which is the majority, right? Because all the interior nodes have no boundary conditions, right? So this would include all the internal nodes, and it would include all the nodes on the boundary that have natural boundary conditions. So this is definitely different from, so this is smaller or equal that number of nodes. So the size is smaller or equal than the number of nodes. And that's the key thing for when I talk about how do you assemble this residual. So that residual gets assembled from the elements, because we can calculate the residual for each element, and then we can put it together into the residual that we actually need to solve for. And the question is, how do we do that bit? Do we assemble this one directly, or do we assemble this one directly? So that's the main question. And the first option that I'm gonna use here is option 1, is assemble, meaning assemble R directly with R with size number of nodes, and then figure out how to reduce that to R. So that would be option 1. All right, so with that out of the way, let's assume that we have boundary conditions in the nodes. So the nodes on the boundary here are 1, 2, 3, and 4, right? And let's assume that we have not essential boundary conditions for all of them. So let's assume that we know the values of these nodes. So one, 2, 3, 4 nodes with EBC, meaning we know the value of the field that we want to calculate in the end. So just keep that in mind. All right, so for the nodes we need the coordinates. Aside from needing the coordinates, they could be numbering any other way. It will be convenient in some cases if all the nodes that have essential boundary conditions are named first, but this is in practice not done, because you would have to reorder the mesh, and it's not necessary. It does give you some advantages in terms of how to split the system at the end. So here, basically, the nodes with EBC appearing first offers some advantages. That I'll explain later. But it's not necessary. All right, so here in this case, they are actually numbered first, all the nodes with the essential boundary condition. Here are the coordinates. For the elements, it also doesn't matter in which order you pick the nodes that form an element. So for example, that's why I stopped writing this and just recording. For element 1, you have nodes 1, 2, 6, and 5. So that's why I wrote here. For element 2, it really doesn't matter as long as you number them counterclockwise. So that's the only requirement, is number nodes counterclockwise. Number nodes counterclockwise. So for element 2, you could do 2, 3, 7, 6, or you could do 3, 7, 6, 2, or you could do 7, 6, 2, 3, or 6, 2, 3, 7. They would all be equivalent. So yeah, that doesn't change. Actually, I have a different one in the example, but let's do 6, 2, 3, 7. Then for element 3, let's do 8, 7, 3, 4. For element 4, let's do 4, 1, 5, 8. So it doesn't matter, it's the same nodes, and the only requirement is that they appear counterclockwise. That's it. And for element 5, let's do this one. It looks nice. 5, 6, 7, 8. So let's just do that. All right, so we have a mesh. We have a mesh where we have the nodes with the coordinates, we have the elements, which is basically just writing out which nodes make up each element. And the one thing that I have here is that I need to know which nodes have an essential boundary condition. And it might be convenient to have those nodes appear first, but it's not necessary. All right, so going on with when you are actually solving the problem, because the whole point of this is the assembly, right? So let's say you are solving the problem, and then you calculate the element residual and the element stiffness matrix. So the element residual for some element, right? So let's assume, okay, let's actually pick one element. For element equal, yeah, I really don't care, but we can do element 1. So for element 1, let's say we calculate the residual, and it's some numbers for whatever reason, like there's like a 3.2, a 1.7, I really don't know, minus 0.6, 1. It's if I'm solving the, so let's say the heat transfer problem, because the that's the only one that I've written the weak form, the residual for. So if you go back to the notes where I define the residual for the heat transfer problem, it's for the quadrilateral element. It has 4 entries because there's 4 shape functions, and so let's assume that you follow those notes. You will end up with some vector that has size 4, and you also end up with a matrix KE that is 4 by 4 with some numbers. I really don't know. 1, 2, 3, 1, 1. Well, 0 will cause trouble there, but 1, 0, 0. Actually, it has to be symmetric. Not necessarily. So 3, 1. It doesn't necessarily have to be symmetric. It's gonna be symmetric for many of the problems that we're interested in. Let's see, 0, 0. Let's just do 1, 1, 1, 0. Just making it up. All right, so we have some residual and some tangent. A 4 by 1 residual, 4 by 4 tangent, and this is for element 1. And now the question, this assembly question, is basically how do we add this to the global residual? And in option 1, this global residual is 8 by 1. Actually, I think it would be convenient to do the residual and the tangent separately. So because this residual is the size, the number of nodes, you can see that each row here corresponds to one node, right? So this global residual is size number of nodes. And so each row on that global residual corresponds to each node. Whereas this residual for element 1 corresponds to the nodes that make up element 1. So which are the nodes that make up element 1? Are 1, 2, 6, 5, exactly as they appear in my definition of the element. And so the assembly is basically just take whatever you have here and add it to the corresponding entry. So this one gets added here. so plus 3.2 to whatever it was already there in that part of the residual. And then the second one gets added to this one. And then the third one gets added here. And the last one gets added here. So that would be the assembly of the residual, for an element. One thing is, hopefully that map is clear. The fact that, and I shouldn't use want to. Oh yeah, it's fine. Hopefully that map is clear. That I'm basically just looking for what is the node number for that makes up that element, and I just took that directly from this element array, and then use that to add to the global residual. That's all I did. So hopefully that is somewhat clear. The question that you might have is, why am I adding it to this global residual? And the answer for that is that if you remember how this was defined, how this residual was defined, this residual, let me move this over here. And let me add slightly more nodes. So why adding RE to I to R? And the answer is because the R definition of R comes from this integral of the domain of the, for example, the K times the gradient of theta times the gradient of shape function A. We actually did it for, I don't know if I wrote the global form. So this, where these would be some global shape functions, but we never define global shape functions. So these would be like some global shape functions. For node A. But in reality, what we defined was RE equals an integral over the element of K gradient theta gradient of NAA. So we only use basically element shape functions. And then obviously because it's convenient to do the integrals over each element separately. But if you look at this definition, then what happens is that now a node has sort of 4 pieces of shape functions. So in this case, in the case where you have these global shape functions, so every node gets only one shape function. So here, we never did this really. Every node would get only one shape function. But that's more difficult to define. Whereas here, every node gets a piece of shape function for every element that it belongs to. So if you think of the elements, the nodes that we have here, so we have some nodes that are shared by several elements, right? So this is the same node. So here, same node in 4 elements. Right, so it's the same node, but it's in 4 elements. 1, 2, 3, 4. So that means that for every element, same node will appear, right? With corresponding element shape function. So I'm using the subscript e to denote the shape function defined only over the element. And so what that means is that now every node, for example, for this node that appears in 4 elements, it should contribute, when you do the integral over element 1, it should add to the same location, and then when you do the integral over element 2, it should also add to the same location, because you will have some part of the integral corresponding with the shape function for this element, for this node, but then same node, but appearing in a different element, will get also part of the residual. So that's the reason why I'm adding to the same location. So just to illustrate that, what happens with the second element? So the second element will share one node. So for element 2, RE and KE, let's say the RE, so this one I'm gonna say R1, R2. So let's say the R2 looks like minus 1, minus 1, minus 1, minus 1. Makes it easy. And then let's write the nodes that make up element 2. 6, 2, 3, 7. 6, 2, 3, 7. So there we go. You see that here now, the first one is 6. So this one should also go to this entry. So that one, when you assemble into the global residual, that one will go to the same place. Also the 2 is shared. Yeah, the 2 is shared. So you can see that actually also this one. So this one will go to here. And the other ones are not shared. So those are new. So this one ends up here. And then the last one ends up here. And so on. You can do that for every element. And so that will be the assembly to this global size R. For the tangent, is the same. You just have to do basically like 2 coordinates. So for element 1, the nodes are 1, 2, 6, 5. So I just need 1, 2, 6, 5, 1, 2, 6, 5. And then I'll have a global K that is size 1, 2, 3, 4, 5, 6, 7, 8 by 8. 1, 2. So for example, this one goes here. I'm not gonna do all of these ones, just illustrate a couple. So this one and this one, so 1, 2, and 2, 1, they go here. Let's say that one goes here, and so on. Well, let's do a couple more. Let's do, now I'm using different colors. Maybe I should be careful. Actually, yes, let me just keep on using well, the off diagonals now make it difficult, because this one should be here. I have to use new colors for I'll use new colors for the off diagonals. Let's do just 2 more. Particularly the off diagonals. I think the diagonals are pretty clear. But let's do, for example, this one. So that will be 1, 6. So 1, 6 and 6, 1. Right, so it's not necessarily that it all go into one block, like it can be scattered around. And then Yeah, I think those are because the 6 5, that part is close, so that one you'll get like some block here in the lower lower right, and so on, right? So you continue doing that, and then similarly you have K2, and let's say that K2 is just some collection of numbers minus 2 0 0 1 0 0 1 3 0 1 0 2 2 2 1, and then here you have 1. Yeah, let's just making it up as we go. And let's write the node numbers for element 2. 6 2 3 7. So 6 2 3 7 6 2 3 7. And again, let's just do a couple, not that many. Let's just do some of the off diagonals. Let's do 3, this guy right here. So that one will be 3 6, right? So that one will go to some place like here, 3 6, and 6 3 6 3. So that's where it would end up. Oh, but 0. So actually you don't have to do those. The 0 ones are not really important. And so on. I guess you get my idea. Here there's gonna be one repetition. So if you go to 2 2, so this one right here. So that one is 2 2. That one will go to the same 2 2 here. So this will be plus 3. So in general, obviously the same thing happened as before. So whenever you have an entry here that goes to the same entry of the global K, same thing, just add them, right? So if they point to the same location, just add them. I don't know if that's the only one. 6 6 obviously will also go to the same location here. And I think that, and the 6 2s as well. So here, some of the diagonals and some of the off diagonals go to the same location. So for example, I didn't do it before, but I'll do it here. So 6 2, right? And where's the other one? Not that one. Yeah, so this one. So these two, and here they also appear, right? So the 2 and the 6, so this one and this one, they are 0. Well, too bad. So those definitely appear, 6 2 and 6 2. So in this case, realigned, it's 0 plus 0, 0 plus 0, right? Because they are also repeated here, so they would add up to the same. In this case, it's 0, so it's not very interesting, but hopefully you get the idea. All right, so that is the assembly form number 1, which is you just assemble a global residual, which is size number of nodes, and a global tangent, which is size number of nodes times number of nodes. All right, so let's stop right here, and then I'll make another video. I'll make 2 more videos for this part. Yeah,